It's because it starts by assuming that objective and subjective are two completely different things, and that objective is something that is achievable, and in order to achieve objective, you have to suppress subjective, right? In order for objective to be efficient, to have a objective narrative of the world, you cannot have any kind of subjectivism in what you're doing, saying, probing, analyzing, or thinking. Can we create then this beautiful rational description of the world? And the intention is wonderful until it doesn't work, right? And it starts not to work when you realize that everything that we do is colored by the lenses of our subjective interaction with the world, right? And you may agree with me that, you know what, Newton's laws are Newton's laws for me, for you, for whoever. You just have to write them down, and there is objectivity in that, and that is true, right? I mean, you can't argue with that, but the context in which these laws were developed and created are not independent of the history and the place and the minds and the personal histories of the people that developed those theories. And so there is a cultural context that comes in with everything that we do. And so to consider science as value free is just a fabrication, which is just not true.
Hello, everybody, and welcome back to Chasing Consciousness. So today, we have the blind spots of Enlightenment science to assess. We're going to be investigating the common belief that science can provide a universal, objective, even godlike perspective of the truth of things independent from our human experience. We're also going to look at the implications of the consensus in science, that all phenomena can be reduced solely to material causes, and what such a worldview might be missing out on. And to assess this, we're going to be looking at data from cosmology, from biology, from cognitive science, and from quantum physics, and thinking about the assumptions they entail that are just so baked into our Western scientific approach that we may have forgotten that they're assumptions at all. Now, in order to do this, we're going to be speaking to the Brazilian professor of theoretical physics at Dartmouth College, Marcelo Gleiser. Marcelo works on a range of topics from cosmology and information theory to the history and philosophy of science and how science and culture interact. He's also the author of many popular science books, including most recently, The Dawn of a Mindful Universe, a Manifesto for Humanity's Future, and his 2024 book, which we'll be focusing on today, The Blind Spot: Why Science Cannot Ignore Human Experience, which he co-authored with the astronomer Adam Frank and philosopher Evan Thompson. Now, I have wanted to speak to Marcelo about the limits of science, about a post-reductionist approach to science, since he was recommended by my previous guest, psychiatrist and brain hemisphere researcher, Dr. Ian McGilchrist, in the Series 1 episode, Navigating Beyond Materialism. So I just can't wait to get into this. So without further ado, let's go. Marcelo Gleiser, welcome to Chasing Consciousness. Thank you so much for coming on the show. How are you today?
I am well. Thank you so much. My pleasure to be with you.
My pleasure to have you, Marcelo. It's been a long time in the waiting. So I absolutely love to start asking my guests to speak about the first burning questions from their lives about life, the universe, and everything when they first became aware of their own thinking, usually sometime between sort of 8 or 12, possibly earlier, as a way of reminding us that despite most published scientists being these kind of lofty intellects, that you were all innocent and in awe of the great mystery, just like us when you were younger. What can you remember from that time that sticks out as meaningful when you look back?
So that's a great question. I would say that my first deeper musings about reality was about the nature of time, because I lost my mom when I was 6 years old. And sort of like the violence of a loss like that when you're so young, that has to do with time, like somebody's here and somebody's not here, made me a very metaphysically and mystical sort of young boy. So I would say, what is time, and does time really end? Do we continue? Is there life after death? All those sort of like not very normal questions for a young boy to ask.
Mm. Okay. So before we get on to your new book, The Blind Spot, Why Science Can't Ignore Human Experience, I want to start by sort of setting the scene of your work in general and your scientific perspective by talking about a few of the ideas from your earlier books and getting a take on some of the key ideas that are relevant to this sort of reductionist debate. Firstly, a tear at the edge of creation. In that book, you call out an old assumption that beauty and symmetry come together. And so we tend to look for symmetry in our theories and when we're looking at nature, and we tend to identify beauty with that kind of order. Now, you argue, on the other hand, that nature is asymmetrical. And in fact, we see nature's intelligent adaptability and dynamism precisely in that asymmetry of complex systems. So tell us a bit about what you argued in that book and how complexity and asymmetry are slowly becoming better understood in science. Dare I say, even they're starting to be thought of as beautiful.
Right. So you're right. We grow up as scientists learning to revere symmetries as an example of the beauty of nature, right? And those symmetries are not necessarily just, a circle is perfect, but there are also mathematical symmetries that we look for in theories because, frankly, they are there. I mean, many, many very powerful theories of nature, mostly in particle physics, how we understand how the elementary blocks of matter interact with one another, do reveal these beautiful mathematical symmetries. And they have been sort of an inspirational piece. I mean, the most famous one is like Paul Dirac in 1929. He brings together quantum physics and special relativity, two new theories at the time. And once he does that, he comes up with two solutions. One, the electron, explaining how the electron behaves. And the other one was a very mysterious particle nobody had ever seen, which was like an electron, but positive charge as opposed to negative charge. And it was like, what is this? And then he says, well, if I take my equation seriously and the symmetries that are in this equation seriously, there has to be another particle, which is just like an electron, but with the opposite electric charge. 3 years later, they discovered the positron. So the power of mathematics is compelling. What is a little dangerous, perhaps, is to overfocus on that as the fundamental nature of reality. That sounds to me like a very Platonist idea that mathematical beauty is only related to that which is symmetrical perfect, which if you go look at the nature of how particles interact and the nature of time, I mentioned to you that time was an important question for me. And indeed, the nature of time is very much the product of fundamental asymmetry of nature, which is we know very well that time only goes forward. And the question is, why does that happen? And if we look at the way particles interact with one another, we find out that the asymmetry of time, that time goes forward, has to do with a very deep and somewhat obscure symmetry of particles themselves, which in our field they call the CP violation, which means charge conjugation and parity violation. Parity means mirror image of one another, and charge means positive, negative. It turns out that those three things, charge conjugation, parity, and time, are deeply related. And the only reason time goes forward is because charge parity, CP, is violated, meaning you cannot create a mirror image of how a particle goes in the world, forward in time. And so the way we picture things is, this is only math though, is that antimatter actually goes backwards in time. It's sort of a very strange idea. But when you put these things together, just to make it the story short, you realize that at the very core of nature, there is this asymmetry. And there are others. Life, the way our molecules of life, our proteins are made of amino acids, and they independently have this, what we call a left-right mirror symmetry. The fancy word is chirality, like chiromancers, they read the palms of our hands. And it turns out that all amino acids, pretty much, that exist in living creatures, from grapes to dinosaurs to humans, are always left-handed. They only appear in one of the two configurations. And this asymmetry of life is also quite mysterious. So what my book tries to show is that there is beauty on the imperfect as well, not just on the perfect. And when I wrote this book, a very interesting thing happened. A lot of people with all different kinds of disabilities wrote to me saying thank you for honoring us, which I thought was quite beautiful and unexpected from my end.
Mm. Okay. Secondly, the island of knowledge, the limits of science and the search for meaning. In this book, you use the analogy of an island of the known world in a vast ocean of the unknown, and how scientism, as we call it, might think that as our knowledge grows, so the ocean shrinks. And eventually we might understand everything through science. But this is actually philosophically incorrect, because our knowledge grows. As it grows, this unveils new questions that we wouldn't have had the scope to ask. And so, in some sense, the more we know, the more we don't know. The more we know, we don't know. And this is actually exactly the point that Ian McGilchrist was making when he recommended your work, Marcelo, that our ability to know, in philosophy, we call this the epistemology, it comes before knowing the thing in and of itself, which is called the ontology. Now, can you tell us how this works? Because it's a bit counterintuitive at first, and why this sort of humble respect for the unknown and the limits of our knowledge is really necessary if science is to actually progress.
Yeah, so you summarized it beautifully. So this book to me is a book that speaks to the very heart and soul of what science is all about, right? Because there was this French philosopher from the late 17th century called Bernard Le Bovier de Fontenelle. And he
Great
wrote,
name. Great name.
the name is beautiful. And he wrote this book the year Newton wrote his Principia, right? The book of motion and gravity. He wrote a book called Conversations on the Plurality of Worlds. And in this book, he asked about life in other worlds, 1686. And his partner in crime was this marquise. So there was a female protagonist, which was very rare at the time. And she's asking all these questions to the philosopher. And one of the questions is, what is philosophy? And the philosopher says, all philosophy is the result of two things only: curiosity and short-sightedness. And I think that's just brilliant, right? Because we humans, we want to know, right? We want to know everything as much as possible, but we can't. We don't have all the answers. We can only see so far with our instruments and with our imagination. And so there's a tension between wanting to know and not being able to know. And I think that defines the nature of knowledge very well. However, with the incredible success of science, people came to believe, wrongly, in my opinion, that we will be able to solve all our technical problems and find the answers for everything, including a theory of all the forces of nature. And even when you go to global warming, the idea that we will solve our problems with technological innovation alone. And those are very problematic points, because if you know anything about epistemology, how we gather knowledge of the world, you realize that that is just never going to be the case, because the very nature of how we acquire knowledge is limited in itself. So, very good example of that historically. When Galileo had his telescope in 1609, he's the first person to point a telescope to the sky. And that instrument allowed him to see things nobody else had ever seen. And that blew his mind more than anybody else's initially. And he saw a whole new universe because of that powerful instrument that he had perfected, which means that those instruments that we use for scientific research, I call them reality amplifiers. They allow you to see more than you have seen before, but never everything. There is the limits of precision of the instrument, and there is the mission of the instrument. Every instrument is designed for a certain purpose, and you can only see so far. So our narrative of reality, I call it a mosaic of ideas. So reality is an ever-going, ever-correcting mosaic of ideas that never really reaches an end, because with every new great innovation, as you said, in this metaphor of the island of knowledge, new questions emerge that could not have been uh, predicted before. For example, we're all talking about information now and AI. Well, 100 years ago or 80 years ago or 6 years ago, nobody was talking that way because those ideas were just not quite there yet, with very, very few visionary exceptions. So the point I'm trying to make with the island of knowledge is, as you said, as we approach our lack of understanding of reality, we should always do that with the humble understanding that everything that we explain of the world is limited. That epistemology, in my opinion, that may shock some philosophers, precedes ontology, because you cannot create a narrative of what the world is made of if you're not interacting with the world directly. So when you say the world is made of atoms, and then you say the world is made of fluids, and then you say the world is made of strings, those ontological substrates of reality, they're shifting in time. They're only shifting in time because we are able to see better and better the substrate of reality. And that's why we can't say anything about strings yet, because we haven't seen them. So to make a long story short, I wanted to point out something. The island of knowledge grows, and the periphery of the island, which is the boundary between the known and the unknown, is always growing with it. And that's the paradox of knowledge that you mentioned before. And importantly, there are also those little regions of the unknowables, lost in the ocean of the unknown, which are questions you may ask about the world, and that you cannot possibly scientifically answer those questions, which I think is fascinating as well.
And this is all part of this sort of embedded perspective from which we come. And I think it's not going to be by any means the last time we come back to it when we get onto the blind spot as well.
Exactly.
Okay, so going back to for a moment, to a tear at the edge of creation, this point about the more you know, the more you don't know, it leads us to abandoning this impossible dream of a theory of everything, right? Carlo Rovelli mentioned here on the show this exact point with reference to the relativity of time, to the uncertainty principle in quantum mechanics, and ultimately to his relational interpretation of quantum mechanics, that the most we can know about any one thing is in its relations to other things rather than in of itself. Now, this is a deeply Buddhist idea, and I know it's had a lot of influence on you, right, Marcelo? And it's this idea that our embedded perspective in the causal chain of things is really fundamental to our scientific conception of those things and inseparable in some sense. Now, you also quote a lot the Zen Buddhist monk on this, Thich Hat Han, and his interbeing concept. Tell us briefly why you think this interbeing concept is so important to the philosophy of science.
Because it brings a perspective about us in the world, which I think is badly needed right now. The narrative that we have constructed through Copernicanism and the Enlightenment is that we are essentially above nature, that we have a perspective on things which gives us the right, so to speak, to almost disconnect ourselves from the rest of the world and tell the story from the human perspective as if this were the only perspective that exists. And I very much disagree with that. And certainly not just the human perspective, but the Western-centric perspective of the world. And so the reason why I like Interbeing is because, and this is a point I make in this book, The Dawn of a Mindful Universe, a lot, which is as you study the history of the universe, and then the history of the formation of stars and solar systems, and then the history of life on our planet, what we find, which I think is really beautiful and moving, really, is this profound interconnection between everything that exists. So within each one of us, and this is beyond Carl Sagan a little bit, between each one of us, we have not just the dust from stars that existed billions and billions of years ago, which is true, right? The calcium in our bones and the iron in our bloods and the carbon, all of this came literally from exploding stars over 5 billion years ago, which is remarkable. So there is Freddie, he's a young guy, but that's just your present, let's say, conglomeration of stuff, that the stuff that you're really made of is billions of years old, and it comes from stars that existed a long time ago. Number one, those stars only happened because the universe has a very specific narrative where it is possible for matter to get together, ignite into stars that have a certain life cycle that creates planets. And then when you transport that to our own particular history here on Earth, right? And we look at the history of life on Earth. Now we don't talk about, certainly not about Adam and Eve or about primates as ancestors. We talk about a less universal common ancestor, so-called Luca, which is a bacterium that existed some 3 billion years ago. So that's our mom, right? So we essentially all life that exists in this planet comes from that creature that existed billions of years ago. And that is a profound interconnection between all life on Earth and our life on Earth to all the stars that existed in our local neighborhood, the ones that exploded 5 billion years ago. So our story is a mirror to the cosmic story. And if that's not enough interbeing, I don't know what would be,
So one of the things you emphasize, and I think scientism sometimes forgets, is that there are lots of different types of knowledge. And because of this huge focus on this sort of propositional knowledge coming from science, we often forget that there are other types, right? And that you say that many of science really can't cover all of these types of knowledge. Can you just give us a quick overview of these different types of knowledge? Because it's an important part of the message, right? That there is a compatibility between science and philosophy and spirituality.
Right. And ancestral knowledge, right? So in a sense, the thing that comes to mind right now to me, because it's so present in my current thinking, is how indigenous cultures relate to nature and how different that is from Western-centric ways of relating to nature, and how we have erased and forgotten those ways as much as possible through our somewhat current history and recent history of a few hundred years, and why we should go back to that, right? And we should go back to that because they look at the world as a sacred place. And a sacred place deserves our respect and deserves our almost veneration as if it's a temple. And we have commodified the world, right? We meaning the Western way of thinking, and not just Western, but the whole agrarian civilization way of doing things. Because, if you tell the history of our species, let's say we've been around for 300,000 years, we meaning the Homo sapiens species. For 290,000 years of that, we were hunter-gatherers. We had a completely different relationship to the world. We evolved in a very different way to be in nature, and we developed an acuity of senses and mobility to exist in their world where we had to hunt and gather and find shelter, etc. And only in the last 10 or 12,000 years, we kind of changed that narrative, right? And notice how interesting that before the agrarian times, there was no real separation between the world of humans and the world of the spirits. I mean, reality was enchanted, right? Everything was alive in a certain way. There was the spirit of the tree, but the tree was my uncle, or the mountain was my cousin. And I have lots of friends who are from indigenous cultures in Brazil in particular, which is where I grew up. And they relate to nature as is a big family, right? And they always said, to me, there has never been a separation between me and the world. But we have created that, funnily enough, and because we have done two things. First of all, we detached ourselves from nature and lost the relational connection to a natural world from which we are completely dependent on, to believe that we are actually above the natural world, that we can, through scientism, we can control nature, we can erase mountains and suck the entrails of the planet to support our project of civilization. So we are definitely above the natural world until comes modern times and we realize that we are not. So going back to the sacred realm of many indigenous cultures, where the nature was not something apart from us, but was something that we belong to. So the notion of belonging and gratitude, to me, is essential right now. And it should be the centerpiece of a change of mindset for us in modern times. And that's where I think. So I call for what I call a resacralization of our planet. That it's what I call a biocentric view of the world, where every planet, not just ours, but this is the only one we know so far that has life. Every planet, every world that has life should be considered a sacred realm because it is the utmost expression of material complexity in the universe to have a matter that is able to think about itself and about reality. And that should give us, this imperative, moral imperative to change the way we relate to the world in a way that we become part of it again, as those people have been telling us for thousands of years.
Many of these ideas you're discussing are in your very recent book, Dawn of a Mindful Universe, from last year. And you speak about many of the things you've already mentioned. But there's a particular point I wanted to pick up from Dawn of a Mindful Universe. You draw attention to our recent sort of fetishization of space colonization and of sci-fi and this high probability that life exists somewhere else in the universe. And you draw attention rather to this actually extremely low chance of life, or at least life as diverse as that we find on our planet existing anywhere, even close by, maybe even in this galaxy. And you also draw attention to the sort of extreme discomfort of other planets as alternatives to our own. And we should just stop romanticizing this idea because basically this place is very, very unique. Tell us what you want particularly.
Oh, this is like my life mission right now, is to kind of rescue Earth as a precious planet, which goes very well with what I was just telling you about. We need to resacralize our planet in a sense that, instead of thinking, okay, let's go from the beginning. So the Copernican narrative, right? Poor Copernicus, he was absolutely right. He said, look, the Earth is not the center, the sun is the center. So Earth becomes a planet, which is absolutely correct, obviously, from an astronomical perspective. But then from that came Copernicanism, which is the notion that not just Earth is a planet, but Earth is a trivial planet, in a sense that there'll be many, many other worlds out there which are Earth-like. And implicit in that affirmation is Earth-like, meaning abodes for life and even complex life, right? And if you start taking that seriously, you have to study what happened to life here on this planet, because that's the only data point, right? And what are the properties that a world needs to have in order to not just have life emerge on it, but sustain it for a very, very long time in order for it to have enough time to complexify, maybe, and become perhaps intelligent. And you go through a list, and I do that very methodically in the book, where you go, can I enumerate some of the steps? And so to illustrate how hard this is.
Actually, that was my next question, which is about fine tuning. So you may want to sort of join those 2 points together because they're very, very strong arguments for something very special going on here. So feel free to tie that in with the fine tuning that really allowed life to happen in the first place.
So I'm going to go with the two of them as you suggest, but I'm going to go against the fine tuning, and I'll explain you why in a second.
Great.
So let's go with just the steps for life, okay, which is fine. So first of all, you have to have the right chemical elements to begin with, like the chemical elements for life as we know it. So carbon, oxygen, hydrogen, nitrogen, and sulfur and phosphate are sort of like the most important ones. So they have to be present. Then they need to organize into simple organic chemicals like methane, which is a carbon and four hydrogens. And from there, they need to go to more complex chemical organics like amino acids. And amino acids need to join themselves into proteins. And then there was the issue of chirality that we still haven't solved how that happened, but that's a separate question. So you go from inorganic chemistry to simple organic chemistry to biochemistry, meaning the fundamental ingredients of the chemicals that biological organisms need. Then, once you have those things, they need to isolate into a protocell, like a little drop, we think, of fat, like lipids. And once they're inside that, there's a boundary between them and the environment outside. And that boundary is protective. And it allows for those chemical elements that are trapped in there to kind of find a way, which we have no clue how it happened, to metabolize energy from the environment, basically eat, and reproduce, duplicate. So that's the protocells. And then those protocells evolved to become the simplest prokaryotic cells, which are the algae and the simple things that were here in this planet for a very long time, for about 2 billion years. Those prokaryotic cells, another mysterious thing that happened, they mutated and became photosynthetic. They 2.5 billion years ago or so, actually more, 3 billion years ago, those cells started to absorb solar energy in order to metabolize. They became light eaters, so to speak. And with that, they released huge amounts of oxygen into the atmosphere, which is kind of a remarkable thing because up to that time, there was only CO2 mostly in the atmosphere, which is not very good for living things. But then with oxygen, oxygen is sort of like the granola bar of organic chemistry, and it allows for a lot of electrons to be deposited on stuff, which allows for more complex metabolisms. So 530 million years ago, there was the Big Bang of biology called the Cambrian explosion, where a huge diversity of life exploded in this planet. And from then on, life became multicellular, more complex. And then the story continues amazingly. You know, the most important that everybody knows about mostly is the dinosaurs and their extinction, right? The dinosaurs, they were around for 150 million years. And then came this big rock 66 million years ago, hit the Earth, changed the planet globally with that impact. And about 70% of life was extinct. The little mammals, which were the rodents only mostly at the time, had no predators. Evolution went through a reset button. Life became more complexified through the mammals. 2-3 million years ago, our biped hominids in Africa emerged. And then 300,000 years ago, we emerged. If all of these contingencies, the photosynthetic mutation, there were 5 large extinctions that happened, the dinosaurs is the last one, caused by the impact. If none of this had happened, we wouldn't be here. So to me, what's truly remarkable about this planet is this level of contingencies that were necessary, that happened, they were not necessary, for life to exist and for complex life to exist and for us to be here. Change a fundamental part of this story, we wouldn't be here.
But you do agree that there is a high probability of other life in the universe somewhere, given the scale of the place.
Yes, so we can qualify that. So there's simple life, like here was bacterial unicellular life for 3 billion years, and there's complex life. So I would say that given that the laws of physics and chemistry are the same across the universe, given that in this time, well, so we believe that's from what we can see, and given that in this galaxy alone there are over 1 trillion planets, chances are, yes, there may be some kind of life out there. Complex multicellular life is another story. Intelligent, technology building life is even another story. So that we have no metric, we have zero ways of measuring how that's possible. So my claim is that even if there is somebody out there that is thinking similar thoughts to the thoughts that we are about. Why are we here? What's the purpose of life? How come there is a universe? What is fine tuning? They'll be so far away that for all practical purposes, we are alone. And knowing that we are alone and knowing that this planet is so rare and special, if we don't do something about it, we are going to basically pressing the mute button on the universe as a whole, because we are the ones telling the story of the universe. So we are, in a sense, the voice that is telling a cosmic story, which is our story. Other aliens out there, if they exist, may tell different stories, but this is ours. And so silencing our voice is a profound crime against the universe as a whole that allowed us to be here.
And I guess that brings us on to another important point that I think makes this rare occurrence of such wide biodiversity even more impressive, which is the remarkable level of fine-tuning in the universe required to allow even basic bacterial life to emerge in the first place. I don't actually know if anyone's tried to calculate the actual odds of such a thing happening. I suppose it's difficult because the context is so huge, but there is also arguments pushing back against it. The anthropic principle, the multiverse lovers who argue that it's not that amazing because we just happen to be in one of the universes where it did happen. But all of that stuff aside, tell us briefly, what is fine tuning from a sort of cosmological point of view, and why is it so extraordinary? And for you personally, what are the implications of the fact that that really did come about so improbably?
So, Freddie, so for me, I am not in awe with fine tuning. In fact, I am a contrarian when it comes to that. And I mentioned that in the Terror the Edge of the Universe, because I'll explain you why. I think about science in a very historical way. And if you look at how we built the scientific narrative of the world, right? It was first to the discovery of the law of gravity, and then we go to electromagnetism, and then we go to these stronger nuclear forces which happen inside the nucleus. And every time we did that, we found out that there are certain constants of nature which are essential for us to tell our story. So the force of gravity, Newton's force, has a G in there, which is the gravitational constant, which tells you how strong gravity is. The electromagnetic force has a constant there that tells you how strong the electric forces are between two charged particles. And the other forces, the strong and nuclear force, strong and weak nuclear forces, have their own, we call them coupling constants. And the electron has a certain mass, the proton has a certain mass. So the fine tuning is this that people talk about, is that if you tweak the values of these fundamental constants, and you can include on that the speed of light or other things, if you tweak the value of these by very, very small amount, and people have done this calculation, you would destabilize stars in such a way or change the rate of expansion of the universe in such a way that you wouldn't form stars, you wouldn't form planets, you wouldn't form life. So the universe seems to be fine-tuned for life to exist. That's the statement that people tend to make, right? And the reason why I disagree with that statement, well, there are several, but First of all, I don't think life is an ubiquitous property of the universe. I think life is an incredibly rare property of the universe. So to say that life is out there is the uber Copernican, it's sort of like they actually, it's even called the mediocrity principle. I don't know if you've ever heard of this in cosmology, which is like Earth is just a mediocre uh, planet, life and observers who are intelligent, the mediocre property because there'll be so many of us. And I think that's just an outrage. We have no idea of that. You cannot use inductive thinking. This is the point. And I'll elaborate if you want. You cannot use induction to say anything about life. You can use induction to say, look, if our sun developed the solar system, similar stars are going to develop other solar systems. So there'll be a bunch of stellar systems out there. That's cool. But to go from there to life, you can't because there is no metric. There is nothing. We do not know how to quantify this jump from abiotic to biotic matter. How the heck a bunch of chemicals suddenly decided that they were alive and had intentionality? Because everything that is alive has intention, right?
Cognition, right?
Cognition, if you're alive, you want to live and you go eat. So a bacterium, you put a bacterium in a solution, there is more sugar on one side, the bacterium is going to go where the food is because it wants to live. How did stuff made of atoms and molecules become aware of its environments, right? So this is a big mystery. And to say that this is an obvious thing that will happen everywhere, we can't.
But the James Webb telescope can now identify in distant solar systems planets that have all of the necessary ingredients in the atmosphere to mean that that is quite probable, even if it is just at a sort of very, very basic bacterial level. Doesn't that change the probabilities at very least, even if we don't have an empirical case to study and compare our biodiversity to? Doesn't that at least give us a stronger probabilistic argument?
So I'm working on that right now. I'm actually working precisely on this. We're looking at data from the James Webb Space Telescope and looking at the composition of the exoplanet, the atmospheres of those faraway planets, and comparing them to Earth at different times of its existence. Because Earth now is one thing, 3 billion years ago it was a very different thing. And what we are finding is that, yes, you can identify certain signatures, we call them biosignatures, like this one has CO2, this one may have some water, but we have not found anything very promising in the sense that in order for life to be there, the planet's atmosphere needs to be out of equilibrium. And what that means, out of chemical equilibrium, what that means, you need pairs of things to be present at the same time. For example, if an alien astronomer looked at us now, and so look at that planet, it has CH4, which is methane, and it has CO2, which is carbon dioxide. One carbon that organizes itself with hydrogen, another one that organizes itself with oxygen. One is non-reduction. So these two things, not to get too technical, are very different chemical animals, so to speak. And they can only coexist in an atmosphere where there is constant formation of organic stuff, which is the CH4, methane.
Marcelo, I have to interrupt a moment and just ask, because I'm sure that there are many listeners like me who just are wondering at the fact that you, through a telescope, are able to determine chemical compositions of atmospheres hundreds of millions of light years away. How the F do you do that?
So it's thousands of light years away. So it's closer to us. How do we do that? It's beautiful. So by the way, Dawn of the Mindful Universe is all about this stuff. So what you do is, it's a beautiful thing. When a planet goes in front of its star, right, it blocks a tiny little bit of the light of that star. This is called transit. And if the planet has an atmosphere, what will happen is, just like the Earth has an atmosphere, some of the light from that star is going to be captured by the chemical elements from the atmosphere. So when you see it from Earth, there's going to be some light of the star that's going to be missing because of the atmosphere. Some of it will be totally blocked out, which is the planet, the rock, say. But some of it is going to go through the atmosphere, filtering through, but a few chemical elements are going to be eaten by the atmosphere. That's called an absorption spectrum, right? And through the missing light that comes from that star, you are able to identify chemical elements because, and this is the beautiful part, that every chemical element emits and absorbs light in a very specific way, sort of like it's called, we call it a chemical fingerprint. So if you warm up hydrogen as a gas and you look at the light that hot hydrogen emits, you find that it emits mostly in the red and there is some green. Those wavelengths of those specific lights are very precise. And so you can do detective work. Look at the atmosphere from the planet. Stuff is missing. What's missing? Oh, there's that wavelength of blue, the wavelength of green. Oh, that's nickel. That's carbon. That's this. And so you're able to decipher.
Well, thank you for clarifying. I've always wondered that. Thank you so much for giving us a layman's definition.
Yeah. So that's where it comes from. Anyway, so back to that story. So the fine tuning, it is, for me, instead of being in awe that the universe is fine tuned to have those constants of nature, the way I look at them is that they were necessary discoveries that we use to build our story of how the universe works. So thinking that the universe could have been different, it doesn't make a lot of sense to me. It's because these are the only constants of nature that we could have measured, because that is what the universe is like.
But this is the anthropic principle, isn't it? This idea that we're already here, and therefore, of course, we're seeing everything from the point of view of somebody who's still here. If I understand correctly, Marcelo, that's what the argument that they call the anthropic principle, isn't it?
Yes, but there is nothing surprising about that. And that's the point. That to me was, so it's sort of like you speak English and you're wandering around the countryside and you go into a library and you don't know what country you're in. And the library has only English books. And you say, look at that. They made these books for me, and how important am I, right? And the point to me is I believe much more in an accidental description of what things are, and to speculate that, well, the constants of nature could have been different. Well, we wouldn't be here. And the multiverse, by the way, it's an interesting story there, because to look at the whole history of string theory and where the multiverse, this particular kind of multiverse, comes from, in the early 80s or mid 80s, when I was doing my PhD, everybody wanted to work on string theory in theoretical physics because it was beautiful. The idea was you would write a single equation. You're going to find a single solution to that equation, and that equation will be our universe. Damn, right? I mean, how can you beat that? No wonder I was like in awe. Yeah, I want to be part of this stuff, right? How you write an equation, you solve it, and here comes our universe. With all the constants, by the way, with the constant of gravity, everything would come from a single parameter, which we call the string tension, which was this number. But from that number, everything else follows. It's just like spectacular. Fast forward 40 years, there is no single solution. There are gazillions of solutions, 10 to 500 or give or take. And so you say that exciting unicity, so to speak, of that theory is thrown away. And so now people that spend their whole careers working on this stuff say, what do I do with this? They say, well, no, this is actually good, because all these different solutions are just other universes. And yes, ours is just one of them. And those other universes just have different properties. And we just happen to be in this one telling the story of this universe, because this is one where we can tell stories because of the constants of nature, as we discussed. Oh, by the way, we can't know if those other universes exist, because we can't go there or receive any information directly from them. But it doesn't matter because the theory is so compelling. And I just don't buy that. I just don't buy that theory at all.
Well, it'll be very interesting, to loop back at the end of the conversation to how you understand the word sacred, because if you're saying that it's all completely by chance and a matter of luck, that such a special thing has evolved in the first place, it'd be interesting to hear and understand how, for you, that translates to a spiritual idea.
Oh, I love that. Can I go now there? Because that's such an awesome thing.
Well, why not? Because we've just discussed this particular book. Why not? Go for it, Marcelo.
Just quickly. So the sacredness here is completely removed from a godlike entity. That's the point. So it's really a secular kind of spirituality where we are in awe with the spectacular beauty of our planet. And that's where the sacredness comes from. It's not about a supernatural design or anything like that, but it's the realization that we humans have this deep, deep connection with the planet. We completely are related to it. We codepend, it coexists with all forms of life here. And that to me is deeply spiritual. And it has nothing to do with a godlike entity. And that's where the sacredness is. It's a modern, post-Copernican, post-Christian, post-monotheistic, post-enlightenment kind of sacredness that relates us back to the sacredness of indigenous cultures that have known this for thousands of years. That's what I meant by that.
Beautiful. So, listeners, Marcelo and we ran out of time, but we were really enjoying our discussion. So we scheduled another chat, and that's why we might sound and look a little bit different. Marcelo's got a beautiful background that he didn't have last time. So that's why we look and sound a little bit different. But we're just going to crack on exactly where we left off. So, Marcelo, with that context of your previous work, your clearly powerful passions and activism, and some ideas that are going to be really key to the main theme of today's discussion, moving towards a sort of post-reductionist science, let's tackle this tricky topic by getting into some of the blind spots in the assumptions of post-enlightenment science, blind spots that astronomer Adam Frank, yourself, and philosopher Evan Thompson speak about in your new book, The Blind Spot: How Science Cannot Ignore Human Experience. Now, before we break down the evidence from astrophysics and biology, quantum physics and cognitive science that you assess in such a detailed way in the book, let's talk about this Enlightenment paradigm that you're kind of all pushing back against. Mm-hmm. So this scientific revolution led to the scientific worldview that we touched on at the start, that science can offer some sort of godlike objective view of reality as a whole, independent of our place in it, and that all things will eventually be describable in scientific terms. Now, a big part of that worldview comes from reductionism, associated with the philosophical position of materialism, that the only thing in the world is matter, and that all phenomena, even complex objects, mental constructs, or even life itself, can be reduced to and explained by smaller physical constituents. Tell us about this rise of reductionism and the emergent properties and higher order objects and living things that put that materialism into question.
Right. So it is really a historical coincidence, perhaps, or perhaps not a coincidence, but a contingency that reductionism was very, very successful because of the way Western science advanced, right? Because if you think about the history, the first thing that scientists really tackled very efficiently were the motions of the skies, like how the planets moved around the sun. Of course, just the transition from Earth center to Sun center was already a watershed, right? I mean, it was like a big, big deal. When Copernicus came up with the idea in 1543, it was actually not the first time that somebody proposed that the sun was the center. There was a Greek guy called Aristarchus of Samos, who around 300 BCE came up with the same idea. But at the time, Aristotelian ideas were so powerful, the dogma was so set, and and this is very important, the kind of like attraction of Aristotelian ideas in terms of they make sense because they are intuitively appealing to us was so widespread that people did not want to abandon all of that in name of some assertion by this guy saying that, you know what, it makes more sense to think of everything revolving around the sun than everything revolving around us, right? And because, Aristotle would say something like, but doesn't make sense because, if I grab something like a pen, like this pen, and I let it go, boom, it's going to go down because it belongs to the earth, because it's made of stuff. And the local place for stuff is on the ground. And so there's a natural motion. That's how Aristotle would define this, that things which are displaced from their normal place of belonging would move naturally too. And that's why a massive object that is suspended in the air will fall down back to the ground. That's why when you light a match, the fire goes up because it's above the air. And so with this sort of very intuitive stuff, right, Aristotle developed a hierarchy, a material hierarchy of the world. So earth, water, air, fire. And the natural motions were based on this very simple way of thinking about, hey, that's what I see. I look out and that's what I see. If I am underwater and I blow a bubble, it goes up because air is above water. Anyway, so these are the natural motions. And this one made so much sense that people said, hey, you don't see anything moving, everything, when you look up at the sky, you see everything moving around us. You see the moon going around us, the sun going around us, the planets and the star. So why would you even think that the earth is not the center? Where is that coming from? It's obviously everything is. So when Copernicus came up with this idea, so nobody paid attention to Aristarchus. Copernicus knew about Aristarchus, but didn't really claim much in terms of this guy had the same idea as I did. But he also did not offer any compelling physical evidence for the sun-centered cosmos that he was proposing. He said it made more sense. He was influenced by the Renaissance. He was, I talk about early 1500s. He was a young man. He went to Rome to study, and he saw a solar eclipse, and he was blown away by the fact that astronomy had evolved to such an extent that we humans could actually predict when something like an eclipse would happen. And we just had one here in the United States. It was just spectacular. I took my sons to see it. Totality. It's something that is deeply moving. Copernicus was deeply moved, not just by the spectacle, but also by the power of reason. This is essential to your answer, to predict how the cosmos behaves, right? And because it looked like a very ordered machine. And so they said, well, after Copernicus, it took a while for people to buy his idea. And we're not going to tell the whole history of how they happened, because there'll be a whole other podcast, but a sequence of Galileo, Kepler, and then Newton, and to a certain extent, Descartes as well. Those people, they solidified the notion that the sun is at the center. And from then on, especially with Newton and his language of forces, so there is a force, an attractive force between everything that has matter, and everything that has matter responds to this force, which is called the force of gravity. And you can actually write equations to explain how powerful this force is when the sun is attracting planets. Or, by the way, I am here in northern United States. You are in Italy, and there is a force of gravity between me and you right now that is connecting us. It's just incredibly weak because we are so far away. But the point here is that everything is connected in the universe by this web of gravity. And Newton came up with this insight, right? And that was very appropriate to him. And I make a point of saying this because he was not just a rational scientist, but he was an alchemist as well. And being an alchemist, the notion that, on earth as in heaven, right? Below as above. Perfect, because it's the same law of gravity that rules how an apple falls to the ground or how the earth goes around the sun.
It's the
And
ultimate
so,
non-local phenomena as well. We
yeah, I
talk
mean,
about
how is,
non-locality in quantum physics as something so amazing, but we forget that gravity itself is the ultimate non-local phenomenon.
in a sense, because, there is a force that is propagating through space, right? That is, in a sense, connecting things which are very far away. So we still would, I think, in a more strict sense, call it local, just because um, you can see how the force changes from point to point in space, so to speak, right? So as you move far away from the source, it gets weaker with the square of the distance, kind of thing.
Mm.
But and then anyway, so the point that I'm trying to make is that it made sense for people to talk about materialism and reductionism, because when you look at how Newton set up his theory of gravity, he simplified things tremendously, right? And I always say that physics is the art of simplification. It really is about getting a very complicated system, strip out everything that is not really necessary to describe how the system works, and then capture the essentials in a model that you can describe mathematically. So that is the heart and soul of what physics is about. So Newton said, look, if I want to calculate how the moon goes around the Earth, all I need is the mass of the Earth, the mass of the moon, and how far away they are from one another. Period. I don't need to know that there are oceans or people on the Earth, that there are mountains or craters on the moon. All of this is excessive baggage that I don't need to explain the very fundamental move. So I can reduce the complicated system, complicated, say, Earth-Moon system, to just three data points: the two masses and the distance. Wow, that's just like mind-blowing, right? And it worked. That's the thing. And then he says, I can use this super simple theory to predict when comets are going to come back, to explain the tides, why there are two high tides a day, to explain why the Earth is tilted on its axis and the precession of the equinoxes. Um, I can explain that the Earth is not a perfect sphere, but it's actually flattened on the poles and elongated on the equator because it's a spinning world. Just like when you make pizza, you spin the dough and it kind of elongates on the equator. All of this stuff came from this super simple theory of gravity that Newton developed, which then became the archetype of a successful simplifying reductionist theory. So the interesting thing about this, and I think this is going to enrich the conversation tremendously, is that if you actually read Newton's papers and his books, he was deeply troubled by his own theory, because he could not understand how could two pieces of stuff exert a force from far away on one another.
That's kind
This,
of what I meant. That's kind of what I meant
that's
about
what I
the
meant by
non-locality, that he
yes,
really, it didn't sit well with him, a little bit the way that Einstein struggled with entanglement. He knew it was real, but he didn't know what to do about it.
nice, because it's true. So it says, how could two things which are so far away, not touching, act on one another in such a decisive way, right? I mean, come on. This is the Earth of, planets going around the sun is like essential. And he says in his book, he says, I feign no hypothesis, meaning I am not going to guess. I'll leave it to the discretion of my readers to kind of determine this. So
Yeah,
that's in his real book.
that's the humility we were talking about earlier, right?
Yeah, yeah, absolutely. And he says, to me, and this is in the real book, then I'm going to tell you about the ladders, but in his book, he says that, and he says, to me, it's enough that my theory explains all of these phenomena that I'm telling you about in this book. So this is the Principia. And this is called the general scholium, the very end of the Principia. He talks about this stuff. So he says, it is strange, but I'm not going to, dabble into this because I don't know what to say. Years later, this is what's cool. This theologian from Oxford called Richard Bentley writes to Newton and says, I want to use your theory to prove the existence of God. And Newton loved it because he was a deeply religious guy too. His tripod, right? I mean, he was God, alchemy, and science. That was Newton's life. And they're all the same thing in his head, right? Because God was permanently present and acting in the universe. God was a mechanic, so to speak, in his way of thinking. And so he says, let's do it. And so, and he writes to Bentley at some point. Bentley asks him, look, how come masses attract one another? What's going on? And he says, it is to me inconceivable that anything material could exert such a force without the action of something which is not material. Meaning, there's much more to the story than I know or that I can tell. But my guess is that there is some kind of supernatural, alchemical something acting to create this force. So
what would he have said to you, Marcelo, if he observed the gravitational waves around the black holes that were observed just a few years ago? What would he have said, do you think?
Well, good question, because what Einstein does is, in a sense, he exercises the no, as you call it, non-locality. Let's call it the action at a distance, the mystery of this weird thing. Einstein said, it's all local, and it's due to the curvature of space. So now gravity is not this mysterious force at a distance, but it is, if you have a material body, it bends space around it, and things move in these patterns because of that bent space. And so I think Newton would be very disappointed because it would take away the magic, right? It would take away the magic, the sort of the enchantment of his theory that allowed him to speculate that there was some very deeply spiritual connection between matter and existence, right? And in a sense, what Einstein does with gravity, and we're going to talk about quantum non-locality later, but what he does with gravity is he exercises this non-locality, or this action at a distance, with his theory of relativity that basically tells you that it is all local. So it's a local theory of space-time, right?
Marcelo, can I just ask you briefly because emergent phenomena are quite important for where we're going to go beyond the sort of classic reductionism, could you separate between what's known as strongly and weakly emergent phenomena, just to give the listeners an idea of where certain phenomena kind of fit slightly more into this reductionist view and others just really seem very odd?
Mm-hmm. So a weak emergent phenomena would be, for example, let's see, the concept of temperature in gases, right? Because if you think of a gas as a collection of molecules that are moving around, like air molecules all over the place here are moving around, if you adopt a reductionistic approach and you say, let's look at one molecule of nitrogen or oxygen, there's no temperature in one molecule. Temperature is a collective effect of many molecules because they need to be interacting with one another. They need to have what we call an average velocity. And then there's an emergent property of a collection of molecules of a gas, which we can call the temperature of the gas. So 1, 2, 3, 5 molecules don't have a temperature. But a gas in a room, which has a trillion or more molecules, then you can talk about this emergent property, which is the temperature, the same with pressure, etc. So you can talk about a global emergent behavior of a collection of many objects, which can be quantified by a single number, which is the temperature in this particular point in space of this gas, right? Global emergence is very different because you can't tell the story from A to B, basically. When you have a weak emergent phenomenon, you're telling a story from A to B. Look, consider a molecule. Now consider 1,000 molecules, and they're scattering with one another, and they're going to have an average velocity. If it's very hot, they move faster. If it's very cold, they move slower. That's the temperature. The temperature is associated with the speed at which these things are moving. So there is a story you can tell, right? And with strong emergence, I'm going to use life as an example of strong
It's
emergence,
a
right?
very good example, isn't it? I was going to say donkeys or,
Right? I mean, how do you go from a bunch of organic molecules to an organism that has intentionality? You cannot tell that story from point A to point B. We have no idea how to connect those 2 points, right? Start with a bunch of proteins, assemble them in a little droplet of usually fat, lipids, and that thing becomes a protocell, and that little cell then decides decides that it needs to reproduce and metabolize energy from the environment. So meaning it becomes alive. That transition is not a story that we can tell, this is once upon a time, this started that way and then it goes that way. So this is a very simplistic way, but I think a very intuitive way of, but to me at least, distinguish between the weak and strong emergence in nature.
Well, it's an important point. And obviously, you've just mentioned one of the big three problems. Now, the first is the origin of the universe, the second, the origin of life, and the third, perhaps the best example of this in terms of strongly emergent phenomena consciousness itself, still a raging debate in all of cognitive science. Now, some scientists, like South African physicist George Ellis, they seize on these higher, strong emergent points, and they argue that these top-down emanations, a classic example would be the mind's thought processes being able to determine changes in the cells of their physical body. And they argue that this downward causation makes it reasonable to believe in a philosophical dualism, a separation between mind and body. Now, that's perhaps a step too far for you and I, because most scientists want to maintain a monism where sort of mind and body are somehow all tied up in the same bag. Neuroscientist Anil Seth used this beautiful image here on the show to explain his view that causation wasn't just firing up or down, it was firing in all different directions, left, right, all kinds of directions. Very neuroscientific analogy. Your co-author in The Blind Spot, Evan Thompson, argues for a kind of deep continuity between all of these levels and directions in some form of monism. How do you personally conceptualize this reduction causation debate? Because it's going to be really important how we formulate this post-reductionist model of reality, right?
Yeah, and let me preface by saying nobody knows anything about this, So it doesn't matter who the person is. The truth is we don't know, right? Which is totally fine, and it's kind of exciting not to know because is the first step towards curiosity, right? If we knew everything, how would we advance knowledge, right? And so we don't know, and the reason we don't know is, well, the biggest challenge with these stories is that we don't know what to tell. One thing, and that's why it was nice to talk about the little molecules of air, and having a temperature when you have a collection of them, because that's the story that is still traceable to a reductionistic narrative. I can still talk, look, there's a bunch of little molecules. They're all like, imagine them as little balls, right? And they're kicking around and scattering around. And because of that, they develop some level of equilibrium, which really means that they have, on average, the same velocity. And we can talk about a temperature. And that's the story that starts with the image of a molecule that is a little ball that we can grab onto, and it's breaking a complicated system into those little parts that interact with one another, and they develop complex behaviors that we can still trace to how those little parts interact with one another.
But it's a picture, it's a story, it's a mental construct. We mustn't forget that. We're going to come back to that.
Yes, that's for sure. When we go to more complicated systems, such as life or definitely mind and consciousness, we don't know how to tell that story anymore, because the same way that you cannot talk about life starting with just proteins, you have much more than that. You cannot talk about mind starting just with a neuron, right? A neuron is not a mind, right? And to say, oh, but they're all connected in some ways, and that tells there's an emergent phenomenon that happens there, and that becomes our mind. It's a nice thing to say, but we have zero conception of what's going on there. So what we know very well now is how to map areas of the brain that are being activated by this or that particular kind of excitation. If it's a sensorial excitation, if it's a noise, or if it's a image, that is going to activate certain areas of the brain. You can map that very nicely, and you can even do things like put a bunch of people listening to the same song in different fMRIs and see which areas of the brain are activated. And what's really remarkable is that some of them are the same because they're hearing, so the auditory cortex will be activated, and that's okay. So that's very objective, and there are a bunch of neurons doing this processing. But then there's the subjective parts, which are going to be different for each individual, that different people are going to react to the same song in different ways. Some people may cry, some people may laugh, some people may be indifferent, and different areas of the brain are going to be activated due to the response to the same stimulus. Is the same song, but obviously the machinery, I think that's a bad word, the complexity of the brain and the mind and the integration and the history of the person and the memories the person has had and the experiences of the person are going to construct a reaction to that stimulus, which is different. And how that construction happens is something that we just don't know exactly how to process or quantify and even qualify, very well.
So you try and avoid finding a story like Evans' deep continuity, or like Annel's multi-directional causality, or like Ellis's downward causation. You try and avoid that kind of simplification because you think it's always just going to be a simplification.
It's interesting you say that, because if you think of a story, right? I mean, when you tell a story, I love this way we're building this whole thing about stories, because I like to think of science and what
But
we
we're
do
story beings. We're story beings before we're data beings. This is one thing that's come up very strongly in the show. We respond more to that. We're designed to respond more to that. Sorry, design is the word there.
Right. But stories are simplifications of things that happen, right? So a story is a reduction of an experience or of a sequence of events, right? Because no story can possibly tell everything that has happened, and that's I just finished teaching a class in my university called Question Reality exclamation mark, and we were talking about the story of what reality is has changed. It's really a mosaic of ideas that shifts in time, right? And the reason for that is that the mapping that we have of reality changes in time, because we can see things now that we couldn't see 100 years ago, 50 years ago, 20 years ago, just because of our tools of exploration change as well. So our stories are always a refinement of reality, but also a simplification of reality, because we can never grasp the whole thing. So, and sometimes It's a very Zen thing. Sometimes, if you don't know exactly what you're going to say, you better not tell the story. And I think when it comes to the mystery of consciousness, and you're chasing consciousness in your show, which is it's a hard chase for sure. You have to have a lot of energy. Um, it's that what we know so far is not enough to weave together a narrative that we can say this is a story that actually summarizes the essential aspects of the reality I'm trying to map. So
Absolutely.
for that reason, I try not to take a lot of. There are some fundamental principles that I do follow when I think about these things, but I haven't gotten to the level of a storytelling yet. You know.
It could be nice also to think of an ecology of stories. And that's why what I mentioned earlier about things being in opposition, speaking to opposing minds, that great minds don't think alike, actually, this ecology is the right place in which to sort of cultivate these stories in opposition. Now, one of the central ideas in the book is that all of our scientific knowledge is firstly phenomenological, i.e., that the data from our instruments comes via our sensorium and our brains modeling the world. And in that sense, we can't really deny its primacy. As the psychiatrist Ian McGilchrist put it in our interview about navigating beyond materialism, the only thing that we can really be sure exists is our experience of the world. And I have to say, I was utterly shocked just earlier today to see Sam Harris on the Rich Roll podcast saying something quite similar, that really this is the only thing we can be sure of. But I imagine that you don't see it in such a consciousness first way. Tell us what you and Adam and Evan, an astrobiologist, a philosopher, and a theoretical physicist, had in common on this idea about the importance of human experience that inspired you to write the book together.
Right. So first, let's go to the experience story, right?
It's the
Because I think that's
subtitle of the book, right?
yeah, it's essential. And we talk about a few phenomenological philosophers like Whitehead, and we talk about Edmund Husserl as well, the German philosopher. And they create expressions like subreptitious substitution and reification of mathematics. And those things are important because what they basically mean is this, and I think that's extremely fundamental, is that point one, we, as Ian already told you, and I agree 100% with that, all we have is our experience of the world firsthand. That's how everything starts. Um, we look, we hear, we touch, we smell, and those things go into our brains, which are these amazing sensors, and get somehow coordinated into an experience of the world. So right now, for example, it's really hot here, right? So it's hot, and I'm looking at you, and I say, I am present. This is the reality that I can sense. And I'm trying to create words to express myself with some meaning towards you. And all of this is happening because I am here with you in this moment now. Now, of course, the way we tell this story can also go into the scientific narrative because I just told you about temperature, and the book starts with a parable of the temperature. Where does that come from? When I told you that you have a bunch of molecules moving around with an average velocity, and that we call the average, actually the square of the average velocity, by the name temperature, we are already going beyond the sensation of hot and cold. But I can tell you, without looking at the thermometer, there must be about in Fahrenheit. There must be about 32 degrees in this room right now, right? And because I have the sensation of heat. The sensation of heat to become translated into the concept of temperature took hundreds of years of science. Because how do you do that? How do you measure? How do you measure this sensation of heat? So Galileo actually created, as being a good Italian, invented the wine thermometer, right? And he saw that alcohol dilates when it gets hot, so you could create some kind of scale and measure that. And so you start to measure heat, which is kind of amazing, or cold, depending on what you want to call, because they're both the same thing, right? Very yin yang, right? The heat, cold. And then the idea of temperature only came really to be understood in a reductionistic way through the motions of molecules much later. But now we forgot, and we will talk about the temperature as something that exists in the world. But the temperature does not exist in the world. The temperature is a construction. What exists in the world is our feeling of hot and cold. So the reification, or let me talk about, so the subreptitious substitution is when you use a concept that was created by a narrative, such as the one I just talked to you about, and give it reality. So now we talk about temperature as something that exists. Temperature doesn't exist. What exists is the. So that is how you go from experience to science to substituting a feeling for a scientific construct of reality. So that's a very simple example. We go back to the orbits of planets and the mathematics of celestial mechanics, which was incredibly successful. After Newton, it became so successful that a bunch of assumptions that Newton had made were unnecessary, including the actions of God to fix, the orbits of planets and to make sure that the first impulse was given by, the angels. Not really, it was just really the formation of the solar system and stuff like that. And so the success of his theory was such that it became more and more formulated in an abstract way. And you go from his simple mechanics to a more abstract mechanics. And then you start to talk about mathematical constructs called Lagrangians and Hamiltonians, which basically encapsulate all this conceptualization of motion in a much more beautiful, elegant, purely mathematical way. And at some point, people forgot that those things were just the consequence of the fact that we actually look up at the sky and see the planets moving, and we can map those motions. And then from there, we can start to create those theories. And they start attributing reality to things which are not real.
To what extent does that mean that consciousness is fundamental to the world? Or again, is that heading straight into the sort of lion's mouth of storytelling where we wouldn't have any way of knowing? Is that where you would stop?
Okay, that's a big jump. So consciousness as fundamental, if you mean as fundamental as matter or mass and electric charge and spin, which is just the angular momentum, the spinning of the particles. Some people that like panpsychism, for example, would say that the reason why consciousness is so complicated is because we're thinking about it the wrong way. We shouldn't be thinking of it as some emergent property of the brain. We should be thinking of it as part of the universe as a whole, just like mass is part of the universe and charge is part of the universe. And there's this thing called consciousness, and matter can, depending on its complexity, matter can, let's say, capture, embrace some of this cosmic consciousness, and to different levels of complexity, depending on the complexity of the material system itself. so that it can then process thoughts in more and more complicated ways. And so people that believe that say, you can think, and I am going to, I'm sure, offend a bunch of philosophers, think of different systems as having different kinds of antennas. And those antennas are the same way that I can feel heat, and that's because of my sensorial feeling of tactile feeling of reality. Maybe we have sensors that can capture some of this cosmic consciousness, which is an ambient thing that exists, just like temperature is an ambient thing that exists. And depending on how complex your antenna is, you can get more and more of it. And if you can get more and more of it, then you develop more and more complex thoughts. And so a very simple amoeba will have some level of consciousness because it has the ability to sense its environment and respond to it. So if you have, a bunch of amoebas in a petri dish and you put a little sugar on one end, they will mobilize and move that way because they want to eat. So they can censor, it's called chemotaxis. So the motion towards chemistry, so a chemically induced motion, because they can eat the sugar and become then, it's an endurance thing.
But it's certainly not, listeners, where we're going with this conversation, but it was just interesting. I just wanted to see if Marcelo got sucked down that route, that, Ian was clear that he was way more than a panpsychist. Bernardo Kastrup, with his very, very interesting, very physics accommodating form of idealism, that in fact all of these physical laws are operating within mind. Very interesting ideas, great episodes on panpsychism with Philip Goff and on idealism with Bernardo Kastrup for any listeners interested in that. But let's come back to the science and to the cognitive physics stuff that Marcelo and Evan and Adam were writing about. Now, in the book, you also list 5 other categories of sort of enlightenment assumptions, apart from reductionism, with blind spots, which I just wanted to touch on very, very briefly. Now, we have a whole episode on the assumptions of Western science, listeners. Really, really interesting philosophy of science episode, if you want to get into depth on that. So we're not going to go into too much detail, but there are just a few in this book that are interesting to list here, some of which you've already mentioned, Marcelo. Firstly, this bifurcation of nature to split between objective and subjective. Secondly, objectivism, the separateness needed in order to be able to observe the rest of the world as something separate. Thirdly, physicalism, more or less this materialism consciousness question we've been discussing in association with reductionism. Fourth, this reification of maths. I absolutely love this surreptitious replacement, what you and Ian call confusing the map with the territory. Fifth, that experience is epiphenomenal. Again, that our experience has no causal influence, which we've already sort of covered when we were talking about upward-downward causation. So I don't want to spend too long on this, Marcelo, as I want to get on to the sort of the post-enlightenment alternative that you're proposing in the book. But I just want to pull out 2 important ideas here. So firstly, on this bifurcation of nature into the objective and the subjective. Now, this does relate to this Buddhist idea of interbeing that we discussed earlier, right? That we inextricably model the world from inside the role we play in it. Tell us a bit why this bifurcation is a bit of a misleading separation.
It's because it starts by assuming that objective and subjective are 2 completely different things, and that objective is something that is achievable, and in order to achieve objective, you have to suppress subjective, right? In order for objective to be efficient, to have a objective narrative of the world, you cannot have any kind of subjectivism in what you're doing, saying, probing, analyzing, or thinking. So, and again, the reason why people believed for so long that objectivism is approachable and doable, it's because when you look up at the skies And it's always about the skies, because so much of the initial development of science had to do with the motions of the heavens. And I go out and I see the moon, you go out and you see the moon, and we both agree that there is a moon there, and we see the moon moving with respect to the earth in certain ways. And you say, yep, you can actually tell a story about the moon that I agree with, that you agree with, because we're both seeing the same thing. So that's independent of me or independent of you, of my story, of your story. It is objective, right? And you say, great. So objectivity works. And because of objectivity works, there is a world out there which is independent of us. And because of that, we should be able to construct a map of that world which is completely independent of humans or how we humans look at the reality. And it's an influential, universal way of thinking. And so any other intelligence, so to speak, that is capable of constructing a map of reality should be able to construct the same narrative as we are constructing, because after all, there is a world out there that is objective and we can map it and quantify it. Then, of course, things get complicated because this dichotomy, objective, subjective, is, in my opinion, false, because you just can't do the separation. So the premise that there is an objective world out there that we humans can map, irrespective of our humanity, that the narrative of reality that we are constructing has nothing to do with being human. It's just a way of intelligence in a universal sense of the word to grasp reality, right? And so that you're separating nature from ourselves. And you're saying that there is a universal mapping of nature, which is the objective mapping of nature, which is independent of the existence of human beings. It's only dependent on the existence of this kind of primal, fundamental intelligence that can see the world in objective ways, right? And that to me is a crime because, first of all, according to the way we look at the world, everything that we do starts with the experience of the world. And so I look at the moon and you look at the moon, that's true. And you can construct stories about the moon, which we can agree upon. We can even create a theory. The beautiful thing about the initial world of science was that the intention there was to create something that would go beyond what people believed in, what party they voted for, what color of skin you have, what language you spoke, how much money you had in the bank. It was this kind of universal way of mapping reality. That is kind of a great call, right? Because after all, how wonderful is it to go beyond all these kind of separations and conflicts that humanity creates for itself in order to create a pure scientific narrative of reality where we can all agree upon, irrespective of our differences. That's the universality of science that has always been, and this is what the Enlightenment is all about. Can we create then this beautiful rational description of the world? And the intention is wonderful until it doesn't work, right? And it starts not to work when you realize that everything that we do is colored by the lenses of our subjective interaction with the world, right? And you may agree with me that, you know what, Newton's laws are Newton's laws for me, for you, for whoever. You just have to write them down, and there is objectivity in that, and that is true, right? I mean, you can't argue with that. But the context in which these laws were developed and created are not independent of the history and the place and the minds and the personal histories of the people that developed those theories. And so there is a cultural context that comes in with everything that we do. And so to consider science as value free is just a fabrication, which is just not true.
It's a little naive. It's definitely a little naive, isn't it?
And as you go into more complicated kinds of science than celestial mechanics, which is in a sense the easiest kind, you realize that the separation between objective and subjective becomes more and more tricky. And so when you go from the question of celestial mechanics to, say, quantum mechanics, right? The study of the behavior of matter at very, very small distances, objectivity and subjectivity get completely blurred. And you just can't construct a theory of quantum mechanics in which you can say is objective, because the way you ask a question about the properties of matter in the world of the very small defines the properties of the world of the very small.
Yeah, take the uncertainty principle as a very, very good example. It's like literally you can't measure two certain things at the same time. You can only measure them one at a time. I think that's just a beautiful, beautiful example of exactly that. And I rather like John Vervaeke's use of the word transjective. So he was looking to reunite these two crucial sides of, he agrees with Evan that it's a deep continuity, that these two things are very much entangled and married and monist. I like this idea of transjective. I keep on forgetting his word and calling it interjective, which is very much like the touch and hand interbeing word you used earlier. Now, Marcel, I'm aware that we're running out of time and I've got to get through so many important things. And I'm going to move us on here because we've spoken about some of these things already. So I just want to make sure that we get through all the juicy stuff before you have to go. Now, I can understand the importance of this primacy of human experience for consciousness studies, for these soft sciences of sociology, of psychology. I mean, you just touched on it here with Newton. I think the listeners and I might need some more examples from nature to understand why this is also important for the hard sciences, like astrophysics and cognitive neuroscience and biology and quantum physics, which is what you guys discuss in the book. Can you give me a few examples of blind spots from those very hard scientific fields, just so the listeners can really visualize why this is a real problem, even in the hard sciences?
Yeah. So basically, you can look at this. So if you have theoretical physics without data, right? So you have a theory that you're building a theory to explain a phenomenon that you don't know what it is yet. For example, let's take an example: dark matter. So dark matter in cosmology and astrophysics is basically a kind of matter that doesn't shine, doesn't produce any kind of electromagnetic radiation. You can't see it, you can't touch it, but it has mass, and so it attracts other kinds of matter that have mass. And so you see it indirectly through its gravitational attraction or actions, so to speak. So we know dark matter is there because you can look, for example, of how stars rotate around a galaxy, and you can map their speeds in which they're doing this. And if dark matter weren't present, there'll be a certain curve that would go from no speed at the center of a galaxy for those stars to more speed, and then eventually going down again as you hit the edge of the galaxy, to something that goes like no speed at the center, and then eventually it tails off and becomes constant. So there is no dropout. So if you use Newton's theory to describe the way stars turn around as a galaxy turns around, like a whirlpool, so to speak, you'd have one curve, and what you observe is a very different curve, which is this flat kind of like, so saying that the stars at the edges of the galaxy move much faster than you would expect. So you attribute that to dark matter, right? And the question then becomes, what is dark matter? Oh, it's a matter that has mass, but it doesn't have any of the other properties of ordinary matter, right? It's what Philip Pullman called dust in his book, his dark materials, which is actually his dark materials for a reason. Anyways, so we don't have any data. So for 40 years, people have been trying to find particles of dark matter, and we haven't found anything. And so theorists extrapolate to create models of what is possible. What is this dark matter? So if you use the models of particle physics that we have now, but you add some stuff to it, then maybe you could justify dark matter. It's just that little bit that is missing from what we call our standard model of particle physics, right? And then you make predictions, and the observers go out there and they don't find it. And then let's move it the other way. Let's go that way. Let's go this way. And in order to create those extrapolations, and this is at the very heart of the scientific enterprise, that you can only invent the new using the old, right? I mean, every new theory is based on an older theory. You can't just jump and invent something else. I mean, when people developed quantum mechanics, they were still using concepts from the other kind of physics. They just added new ways of thinking about it. So Einstein says light is a wave and a particle. Well, waves and particles existed before. He just said that you could be both at the same time, which was weird and new, but it wasn't like it's a third thing that is neither wave or particle, so to speak, right? So every theory that we create is an extrapolation of what we know. And the more advanced theories extrapolate so far away from the reality that we know, they start to pontificate about the possibility of things existing that we have zero idea if they exist or not. But culturally, these ideas, they aggregate value in the community, and they begin to be treated as if they are real. So more and more people work on them and believe in them, and they become almost like a dogma. Example,
String theory.
super theory.
I knew you were going to say that.
You got it. So string theory, I grew up with this thing. I did my PhD on it because that was the thing to do in the 1980s. It was this beautiful thing that if we could just write this equation of string theory, we would find a single solution, and that solution would be our universe. Wow. I mean, with all the forces that we know of, all the particles, how beautiful is that? Can you imagine? That would be the utmost Platonic validation of reality. Everything's about geometry and fundamental. That is the map of the world. We figured it out. But as time went by, and it became a dogma. The ideas of this theory that you need more than 3 spatial dimensions. So you need not just north, south, east, west, up, down, but you need another 6 dimensions that you don't see, because they're submicroscopic. They're just curled up in little balls, that you don't see. So every point in space has a little hidden extra dimensional space of 6 dimensions attached to it. But they're so small, it doesn't matter. And we don't see them anyways. And then one more thing, the super and superstrings come from an additional symmetry of nature called supersymmetry. And so, which predicted dark matter particles. So beautiful, I mean, wow, we solved the universe and we find the dark matter particles. So it was a great idea. It just didn't work, and it hasn't worked for 70 years. And so you start to say, maybe you're really wrong. And the question then becomes, how do you break the dogma? Because the theories became so compelling, so beautiful, that the mathematics became reified, and they became basically parts of reality, even though they don't exist.
But isn't there an interesting point here that the longer that goes on and the more people that get in, so there's a question of kind of forgetting that it was just a theory in the first place that we were still lacking evidence on because it's been so long. And then there's the consensus question. It's like the more people who get on board with something, the more it's kind of like, well, I'm in the club, so I'm okay. I'm one of the gang. That for me is very, very human, not scientific. This is classic tribal mentality. That's a big blind spot, right?
Yes. And it's the iconization of certain people, very bright guys that work on this and are very compelling speakers and come up and truly enchant the younger audiences with like these beautiful ideas of reality, and you follow the cult, and it becomes a cult.
But that's maths. So we can kind of understand the mental construct really, really clearly there. But there are also examples from biology. Give us an example from the more sort of biological side, because in science we tend to see biology as more of a done deal, don't we?
Yeah. So in biology, certainly in the origin of life community, there is this thing called the RNA world. So the RNA world is basically this idea that RNA is the real molecule that matter when life began, because it can be both the protein maker and the transmitter of genetic information. So it's like everything in one, and it works and that way. And people have done spectacular experiments in the laboratory to show how these different RNA molecules can change on the fly and interact with one another. And so people then begin to talk about the RNA world scenario, where the origin of life is attributed to RNA. And and this is essential, because you can do experiments with RNA molecules, it becomes a way of probing this idea. And because it's so efficient, you get grants to do it. And then the whole scientific community mobilizes about the RNA world, even though even though if you start to really think about the origin of life from the beginning, right? You look at an RNA molecule and say, wait a second, RNAs are incredibly complicated things. There is no way that when you go from the simplest amino acids and proteins 4 billion years ago, an RNA was the first way that genetic information was transmitted from one molecule to another, because you're basically creating, it's like this: you are driving a Ferrari and explaining the history of automobiles with a Ferrari, and wait, what happened to the bicycle, the tricycle, the old steam engines, slow. And there's no way that life started with a Ferrari. There's no way cars started with a Ferrari.
You gave the example earlier of bacterium, like very early bacterium being our mom. It's like saying, oh, look, there's us. That can explain bacteria. It just doesn't work that way around, right?
Exactly. So to get to that bacterium, a lot of stuff happened. And so studying RNA to explain the origin of life is just the wrong problem. You can study RNA to explain how life, duplicates and the functions of RNA molecules in many different ways. And now you talk about epigenetics and all sorts of stuff. But that's not going to tell you anything about the origin of life itself, because the jump is too big. And it's the same with the reification of very complicated mathematical structures to explain physical reality through string theory.
Well, Marcelo, I have to say, I'm actually not feeling at all bad about the fact that we're running out of time again, because it's a delightful excuse to invite you back yet again for a further interview, which we're definitely going to do, because I'm going to come and visit you at your new center up in North Italy, which I believe is called the Island of Knowledge. And we're definitely going to be talking about that. But listeners, don't worry, because there's lots more that I want to get into with Marcelo in this further interview. I particularly want to come back to the interface between the sacred, the philosophical, and the scientific, which is something that Marcelo is very, very famous for, and what he basically became the Templeton Prize winner for. So we're going to come back to that in a further interview. So we're going to stick with the science for the last couple of questions, but don't worry, there's plenty more to come when we go and visit Marcelo in situ. It'll be great to do a podcast in situ for a change. Now, because this is so important, everything we've been thinking about, in fact, everything we think about because we're embodied creatures, is based on time. So I just want to take this little sidestep into time, because I picked up on something you said earlier right at the start, and it slightly troubled me. So I want to come back to this. I want to talk about it in the context of observer theory and in the context of entropy as well, because it's come up a few times on the show, a little unconventionally. I really want to get your opinion on it before you have to go. Now, you've said that the arrow of time is very much a real phenomenon, but we've done shows on Einstein, and we've learned that actually it's only perceived to be a constant, an arrow of time, and it's in fact passing at different rates in different parts of the universe, depending on gravity and speed. So here on the show, Carlo Rovelli spoke of letting go of this sense of universal time that modern physics has clearly proved to be false. So I think perhaps what we really mean when we talk about time only going in one direction is the reality of entropy, the second law of thermodynamics, which is just so clearly visible, in our lives with biological aging. And we see it in physics now with this ever slow dissipation of energy out into more and more uniform dissipation. Do you disagree with Carlo Rovelli on this time question? Because it seems to me that the arrow of time is one of the blind spots.
So it's no coincidence that we started the Blind Spot book talking about time. It's the first thing that we do.
It's the first thing we talked about in this interview.
Yeah. So let me clarify something about universal time, because I think there may be a little bit of a confusion here, and maybe I don't know what time was Carlo talking about. I've known Carlo since we're like young students doing our PhDs actually, so it's a long time ago. So nowadays, because of the expansion of the universe, okay, we have to talk about cosmology to talk about this stuff. The fact that the universe is expanding at a certain rate, which is accelerating, that's another big mystery, is dark energy. We haven't even mentioned that stuff, but it's going. There is a universal time in the sense of how far away these galaxies are getting as time goes by. So there is something called the cosmological time arrow, right? Which is simply the fact that things are changing on the large scale, which is the universe itself. And time is really a measure of change, right? So if something is changing, you can attribute a clock to it. And the universe is changing, is expanding. And so when I refer to universal time, I mean the cosmological time, meaning from when we say, oh, the Big Bang happened 13.8 billion years ago. What's that? That's the time, right? And there's a history we tell, oh, the first atoms of hydrogen happened when the universe was 400,000 years old. What's that? That's the time. From where? From the Big Bang. When did the Earth form and the solar system? 4.6 billion years ago. So we time those things because there is a cosmological time, period. And that one has nothing to do with us. It's just happening, because the universe is growing. Now, because matter bends space, it also alters the flow of time itself. So, for example, if I get a clock here on Earth and the same clock on the surface of the sun, assuming the clock would work, time there would tick slower than here, simply because gravity slows down time. So that's a local, maybe that's what Carlo is talking about. There is this local time variation that has to do with the fact that mass affects the flow of time and the curvature of space. Ultimate limit is a black hole, of course, right? So for someone that sees a clock falling into a black hole, as the clock approaches the black hole, is going to go to this thing called the event horizon. And at that point, time, for those of us lucky that are looking at this thing falling in, time stops. So, and then it goes into the black hole, and we have no idea what happens inside the event horizon. But that's all relative, because if you are falling into a black hole, your time does not stop at all. So only the clock. So it's really the relative perception of time that is being affected by these masses, etc. So that's the local time.
But does that connect with entropy? Because in some sense, this cosmological time you're referring to, we can only really measure that change in terms of entropy, right?
Yeah. So the cosmic time has definitely a connection with entropy. And one of the biggest mysteries in cosmology is the following. In order to explain the universe that we have now, an old universe with almost 14 billion years of age, bunch of stars and galaxies, etc., close to the beginning, the universe had to have a very small amount of entropy because the entropy has to grow, right? And the question is, why? What set that small amount of entropy at the beginning or very close to the beginning of time? That's called the entropy problem. So yes, there is a cosmic entropic issue, well, not issue, it's just that time is going, entropy is growing, because as you said, when you formulated your question, we live in this very special window of opportunity where matter can still be organized enough to give rise to stars and planets and people. Earlier on in the universe, there was no such thing. There were no stars. There was definitely nothing like that. No people, no planets. Now we have this, but eventually stars are going to keep evolving, producing more entropy. They're going to explode. And eventually there's going to be this kind of like very boring future. You're talking about trillions of years from now, where no more structure is possible simply because entropy is going to keep growing and growing and growing. And entropy and complexity are incompatible.
Now, this
Right?
brings me on to the idea that I wanted to run past you, this other idea from physicist Stephen Wolfram, who we spoke to in this series, and he defined time in that way regarding entropy. And he's just written a book called The Second Law, which is basically his lifelong obsession since he was 15, trying to understand this entropy problem. And he finally thinks he's got it, and he wrote a book about it. And it follows his observer theory that we're embedded in space and time, and therefore, this is his terminology, we're computationally bounded to our perspective within it because we've got our computational limits. And he argues that for any sufficiently computationally unbounded entity, so imagine some entity that was just way more intelligent or not bound to space and time in the way that we are, entropy wouldn't appear to exist, because he says that all the data about the order of that system is still in there, encoded even in this very, very high entropy situation. It's just our computationally bounded view of that system that makes it appear to be completely disordered and having no structure. What's your take on Stephen's quite interestingly different interpretation of the second law, being dependent on everything we've been speaking about today, which is our embedded perspective right here, rather than any universal understanding of entropy and time as a result?
Okay. So I don't know the idea very well. I never heard of it before. I should read Wolfram's book.
Well,
I
no,
don't
and
know.
he's got a great, his observer theory blog post. A lot of his new ideas as he's coming up with them. He's very, very open to changing ideas. I love Stephen for that. Is on his website. You know, they're short, well, relatively short articles. But yeah, I think this book is a kind of a sum of many, many years of serious head scratching about entropy. So I think it is quite unique.
Yeah, but my first gut reaction is the following: unless you're dealing with complete science fiction scenarios, any kind of life form that is able to develop intelligence is going to do so by increasing entropy around it. There is no way out. To
Yeah.
go out of that is to escape, is to try to bypass the second law. And how could you possibly do that? Because the only way intelligence emerges is through biological interactions, right?
Metabolism.
At least, yeah, you need to have a creature to become intelligence in order for intelligence to exist. If the creature eventually creates some non-carbon based existence
Artificial
at a,
superintelligence, perhaps?
or something like that, right? Then you're talking about a reality which is so detached from ours that I don't know exactly how to quantify that, and I think that neither does Steve. I have to see what he has to say about that. But the point to me is that going back to our storytelling in the beginning, the story that we know right now about life is that life starts with biochemical reactions those biochemical reactions can only happen if they increase the entropy around them because they're metabolizing energy. And intelligence is another way of using energy, to create information, and that information also creates entropy. So I don't know exactly what he means by some super intelligence that does not create or
It,
generate.
it is definitely somebody who's spent their life working on computer systems and therefore not biological system talking here. It's very hard to follow Stephen's thinking, but actually at an imagination level, and as we know, science is born, new scientific innovation is born out of the ability to really let go of our attachments to our previous ideas. And I think when time and the flow of ideas evolving over time and life evolving over time, we're so attached to that. I think when we get to ideas like entropy, it gets particularly difficult. And there's another episode, listeners, in this series, which I don't have time to ask Marcelo about now, about time symmetry and the possibility of time waves moving back. And this very, very interesting Kramer interpretation, the quantum handshake interpretation of quantum mechanics, which involves time symmetry, starts to really throw everything up in the air and all of our very, very intuitive ideas about time and causation into the mix. And yeah, it'd be very, very interesting to get your ideas one day about Stephen's interpretation there. And also Daniel Sheen at the University of California or San Diego, University of San Diego, he's working on retrocausation, and he's had several conferences on these very, very bizarre time symmetry effects, which really are damning. And he also has examples in the lab, very rare, very peculiar lab examples of violations of the second law. Very weird stuff, listeners. So do come back and check in on that retrocausation episode. So we've run out of time again, Marcelo. We are absolutely terrible. We just totally get into this, don't we? I wanted to ask you about some stuff. So I think our next episode should be, Marcelo, about non-Western science. And there's some interesting indigenous science thinkers that I want to get on the show, because we're so tied up in a Western scientific view and that hubris and that sort of illusion of objective, like this is the objective way of doing science and everything else is just to be thrown out. Vedic science, Chinese science, indigenous worldviews is something I really wanted to get your view on. So I'm going to invite you back for another show in a couple of seasons, if that's all right with you, Marcelo. So Thank you so much for your time. Just to close, tell us briefly, you're moving to Italy. We're going to be almost neighbors. Tell us a little bit about the Island of Knowledge and your new position at the University of Siena, just to say goodbye, Marcelo.
Sure. So Siena, so I'll be a visiting professor at the University of Siena, which is about 20 minutes from my house. We just bought this 16th century villa that comes with a church, and I'm transforming that church into what I called a retreat, a transformative retreat for human flourishing. And so if your listeners go to theislandofknowledge.com, the island of knowledge, one word, they will see more or less what we're trying to do. And I just got a very, very big grant to create a think tank there where we're going to address some of these questions. For example, the question of time. I'd like to tell to Steve Wolfram that every computer gets hot for a certain reason, and that's the second law of thermodynamics. And you cannot get around information generating heat. And so there is an issue there, but still, so the Island of Knowledge is just a place where we're going to have this think tank, but also retreats for corporate leadership. They're more aligned with 21st century systemic thinking about the natural world and leadership, which I think is extremely necessary right now.
Ethical capitalism, right?
Yeah, sort of going a little bit beyond the way things have been going right now. So it's a bit of an attempt to shake off the enlightenment and the roots of our Western society in ways which are constructive and I believe more in sync with what we're seeing of the natural world right now, and of modern science as well, which we're pushing towards a more human way of thinking about what science is. as
Well,
opposed to
Marcelo, it is so. Thank you so much for your time. It has been such an inspiration to wax lyrical with you, and I just can't wait to come back and finish this conversation. I've got 3 or 4 burning questions, mostly about this humanist interface, how we can use science, how we can unsilo all of this information, put it to the common good, get these different departments working together to solve some of our greatest problems. And you are an absolute innovator in the field. So it's a great inspiration. So on behalf of the listeners, thank you, Marcelo.
My pleasure. Yeah, let's talk about how the blind spot, planetary blind spot, could be the end of the world as we know it and why we have to address it quickly. That's a big one.